All right, let's get going. Today we're going to be talking about doing hierarchical models using the brms package, which, as you'll see, is very similar to the syntax we use when specifying hierarchical models with the rstand-arm package on Tuesday. As always, when you do things with brms, it's going to generate the code locally and compile it, which means you have opportunity to do a lot more different types of models, even though I think most of the ones today could be done with rstand-arm just as well, but it's good to see it both ways. It's also another opportunity to reinforce the idea of using hierarchical models. And basically, Bayesian models, when in an applied setting, when you're doing research, are almost always hierarchical in some form or another. That just means that your prior on one parameter depends on another unknown parameter, and you're going to estimate the joint distribution of all the unknowns conditional on all the knowns. And so that is not terribly difficult to do, but the discussion of hierarchical models, like everything else, is dominated by their use and misuse, more misuse than use, from a frequentist perspective, when the easiest way to justify something like that is when you have a two-stage cluster sampling design. And so the groups that are chosen to be sampled at the first stage are random. And if you were to conduct the whole research over and over again, you would be getting different realizations from the first stage groups as well as the second stage realizations within those groups. But from a Bayesian perspective, all hierarchical, you don't have to have a cluster two-stage sampling design. Yeah, you have a question?
Yeah, on the cluster stage randomized sampling design. So does this include repeated measures? If I have, say, I sample like 20 school teachers and I want to know how their students do over like 5 years, those repeated measures nested within the teachers, is that considered a two-stage cluster size? However you say it.
Yep. So you can definitely specify a hierarchical model from that sense from a Bayesian perspective, just that there's heterogeneity from one teacher to the next that you want to allow for in the model. From a strictly frequentist perspective, it's nonsense to estimate a hierarchical model in that situation because your research design fixed the teachers. And you're getting new students each year. And so you're making inference on those particular teachers or the parameters governing, you may have demographic information or qualification information on the teachers. But then you're just doing the analysis conditional on the teachers and the asymptotics as the number of students within each teacher goes to infinity. What is an important aspect of these cluster, true cluster, like take a sample of the number of counties, like 50 counties or something in the United States, and then like get data within those counties on people, is to be able to say something about the distribution, the prediction of a new group. And so if you do one of these fixed units designs and you like get your 20 teachers or whatever, you can make a lot of inferences about those particular teachers, but your design is not equipped for you to say something about a new teacher because your design fixed those. And so, but from a Bayesian perspective, that distinction doesn't matter at all because we're not worried about the properties of our estimator if we were to do the analysis over and over and over again. We're just doing the analysis once. We're conditioning on the data that we have. And if we believe that there's heterogeneity in the data generating process from one group to the next or one teacher to the next, then we need to allow for that in the model and estimate the degree to which there is heterogeneity across those. And so, you'll see studies that do like you know, they say they do random effects, which is to say include a separate intercept for each of the 50 states. And that's just, you know, bizarre, because the number of states in the United States has been fixed for like almost 100 years, or not 100, but whenever Alaska became a state. It hasn't changed recently. The only like possible additional states that anybody can contemplate are DC and Puerto Rico. But there's no sense in which like Mississippi and like Tennessee and Idaho and whatever are, and the other 47 states are a sample from like potential states, or anything like that. And so all of those, if you were to do them from a frequentist perspective, and this is more common in economics than in other fields, would be to treat those upper level units as fixed, and then, you know, people within those states as random, and justify your estimator asymptotically as the number of people within each state goes to infinity, rather than worrying about the asymptotics as the number of states in the United States goes to infinity, which isn't going to happen unless we start colonizing the moon and a bunch of other places. So a lot of this turns from the frequentist perspective as to what would change randomly and what wouldn't if we were to repeat this design. But that doesn't matter from a Bayesian perspective, because we're only conditioning on the data that we have and not worried about the properties, you know, for replications of the design that nobody's going to do. Other questions?
So, you know, I feel like if you have 50 states, the frequentist would say that, okay, sure, I'm not going to have 50 other states, but I can have other combinations of like different years, different political climates, different people within those states. So then they have really a fixed effects case, but they treat it random.
Yes.
For this kind of silly conjuring of logic.
Yeah.
And you're saying that is perhaps somewhat twisted.
Well, I'm saying a strict frequentist would say that's twisted. Like there's no randomization of the political climates. Those just sort of ebb and flow historically. I'm just saying, okay, you know, like it makes more sense from the researcher's perspective than it does from a frequentist methodologist perspective. If the frequentist, or if the, you know, researcher would just say, okay, I'm going to do this in BRMS, or I'm going to do this in R-stan-arm, and say these are my beliefs about the parameters and the heterogeneity, just, you know, conditional on the data that I have, without requiring this additional thing that, you know, what parts of my design are a random sample from some population. But, you know, basically none of macroeconomics is a random sample from anything. You know, when people get data, they just like go to the internet and they're like, they go to the website that has data on US GDP or something like that. And they don't take a sample of like years or quarters or anything like that. They just say, give me all the data that you have, which, you know, goes back to shortly after World War II or something like that. So, you know, in what sense are the years from like 1948 to 2018 a random sample of years? Like, it just doesn't make sense. Even though, you know, strictly speaking, that's what, you know, the analysis that they're, you know, doing requires, to think of the period from 1948 to 2018 as a random sample of size 1 from all years binned into a stretch of 70 or something like that. And it just, you know, sort of boggles the mind as to why you would, you know, think of things that way. And that's, you know, only because, well, they're, you know, technically talking about the properties of estimators rather than talking about distributions of beliefs, about parameters, or about hypotheses conditional on the data. And this, I think, gets to one of the, so yes, hierarchical models are a core part of Bayesian analysis. You almost never see a non-hierarchical Bayesian analysis except in like toy introductory examples. But in actual research, it's almost always a hierarchical model. And so in that sense, hierarchical models are very core to Bayesian analysis, but that's because the thinking that motivates hierarchical models is very applicable to a lot of situations, particularly those in the social sciences, where anything involving people or involving things designed by people or created by people, it's unreasonable to assume that the data generating process is exactly the same for all people. Whether we're talking about like psychology or political behavior or microeconomic responses in the labor market, it's just not consistent with data or any sort of theory or with qualitative research to say all people react the same way to whatever. So there's heterogeneity in the data generating processes, maybe a lot, but it's equally unreasonable to say that you learn, nothing about one person from the responses of another person. And so the flip side of this coin is, well, yes, people are not exactly the same. They don't respond exactly the same way, but the way in which people respond is not fundamentally different from one person to the next. It's more a question of degree than it is a question of just a fundamental like discontinuity between how one person conditional on other things like what state they live in and stuff like that responds totally differently from another person in another state. And so this idea of heterogeneity in the data generating process, but relatively small, or at least stuff that we can describe as a continuum of heterogeneity, is really, I think, a fundamental aspect of social science and a bit distinct from maybe some other areas where quantitative methods are applied. And so, like in the case of physics, gravity works literally the same way for, the same size mass being the same distance away from, it would be inconsistent with physics to be like, well, this ball, it's affected by gravity differently than like this other ball when they're the same size away from the Earth, or something like that. And you can go through in other ways, but when thinking about these ideas and what are the most appropriate ones for applying them to the social sciences, it helps to recognize or remember or maybe learn for the first time that the frequentist methods that really dominated the 1900s, including the sort of 1950 to 2000 period in which social science kind of became a thing, were using methods that were not designed for social sciences. They were using methods that Fisher and other people like him came up with, mostly thinking about it in the context of agricultural experiments, mostly thinking in context in which the researcher doing the analysis had the ability to exercise a lot more control about what the values of the predictors would be and even randomize them than what most social sciences researchers had the ability to do, which is, for the most part, stuck with the observational data that you have. Maybe you could randomize one variable, but you certainly can't go back and randomize someone's background or their race or their gender, or other things like that that might be fundamental to a more social scientific analysis of these sorts of things. And so it's not that Fisher was crazy or didn't understand the implications of what he was saying. Of all the things that are wrong with Fisher, like lack of a recognition of what he was talking about is not one of them. It was just the methods that he sort of came up with were more geared toward a particular context and had, social science wasn't even a thing then. But other people picked up those methods in the 1960s, 1970s or whatever, and sort of uncritically, not that they really could have done a Bayesian analysis back then, but weren't critical enough about exporting those methods to the social sciences. Also, has to be said that when they were coming up with things in the 1920s, they didn't have computers or any capacity to do sort of massive number of calculations. And so they were limiting themselves to relatively simple models that either had an analytical solution or a good approximation to the solution that could be calculated relatively simply, on paper. And then, they sort of took the idea of maximum likelihood when computers came around and started applying it in a lot more areas where, maybe in substantive terms, it didn't make as much sense to be applying those things to, such as a lot of things in the social science. When the Bayesian technology caught up, and, arguably it didn't really catch up until Stan came around, a lot of these frequentist practices and some of the supervised learning practices were, already sufficiently entrenched that it's been hard to, dislodge them. But, there's too many people coming to the QMSS program that are unbalanced in their interests and way more interested in learning about quantitative methods than they are applying those to social sciences. And they get, irritated when people like me say, well, that's something that could be applied for, self-driving cars, or, teaching a computer how to play chess, or, recognizing images or something like that. But this isn't the department for, applying quantitative methods for self-driving cars. It's the QMSS. And so those sorts of things where characterized by a lot of signal relative to the noise, particularly versus, the self-driving car thing, they have problems that their signal is not as high as it needs to be in order to avoid, hitting random pedestrians and stuff like that. But they're trying to get there. But, for something like chess, where one, it's a discrete space. It's a huge discrete space in terms of the number of positions, but it's a discrete space. And, there's a clear defined winner, or it's a draw, which is also clearly defined. And so it lends itself to the sort of brute force calculations that, Google and other places that program computers have gotten, pretty good at now. But there's, no real uncertainty as to who won a chess match by the time it's over. And in contrast to a lot of things in social sciences, where there's way more heterogeneity than there is on a chessboard. And it's a continuum of parameter spaces rather than a discrete, 8x8 thing with, 2 colors. Or, all sorts of other things that make, a good R-squared in psychology like 0.1, as opposed to, something that has like 0.01 or something like that, error in it, which is where a lot of the machine learning things thrive. Situations in which you can sort of get away with ignoring the uncertainty in the parameter estimates because it's just negligible. For data generating processes that arise out of machines or other things that have a lot of homogeneity to it that just don't describe social science that well. And that's one of the things that's come out of the discussion about what to do with p-values and embracing uncertainty and all that, is if you have a method and it just systematically ignores uncertainty or doesn't talk about the relevant uncertainty. So a lot of stuff in supervised learning just says, okay, we're going to ignore this, and stuff in, frequentist methods and things like that. Okay, we'll talk about the uncertainty in the estimator across data sets, but not uncertainty in the parameters conditional on the data. But if you're not really like recognizing that uncertainty and trying to capture how much it is as well as you can, and propagating all that uncertainty that you have forward into your conclusions and the decisions and the actions that you make, then you're not doing science, social science or otherwise. Like, that's an important core part of science, is understanding how much uncertainty you have, being honest about it, and not just saying, well, there are conditions under which it might be kind of negligible, and so I'll just, assert that those conditions apply in the situations that I'm doing research on without any sort of evidence. And so I think that is the sense in which the Bayesian approach is particularly useful for social sciences. I think it's useful for a lot of things that are not the social sciences, but I think it's pretty, if you were going to make the case, like, where should Bayesian methods be applied, the first place you would be starting with would be something like social science, because of the nature of it. And hierarchical models are a really fundamental part of the Bayesian approach that, work well with these sorts of social science analysis. And so I've already said plenty of things without disclosing again that, this is Columbia. Talking about Stan, Columbia seeks a lot of grants to develop Stan, use Stan a lot outside of Columbia. That creates the appearance of a conflict of interest, but all the stuff that I said before about the Bayesian approach, yeah, I was implicitly saying you should do the analysis with Stan, but it was more a question of how you should, be thinking about things. Stan is sort of merely a really good way of getting draws from the posterior distribution. But you have to make up your mind that drawing from the posterior distribution is what you want to do, because there's a lot of methods, even, methods that people say, okay, this is like Bayesian machine learning or something like that, that don't actually draw from a posterior distribution and aren't taking that uncertainty in the posterior distribution seriously. So what we want to talk about today is how to do stuff like this using the BRMS package. And as you saw in the reading for today, so Richard McElreath has this great book, Rethinking Statistics, that talks a lot about hierarchical models and actually has a lot of code for estimating those. But it's using his Rethinking package to do so, which has its sort of own syntax. It's a little bit more like the syntax that had been used previously in bugs and JAGs and whatnot. And so we're mostly writing, when we do homeworks and stuff like that, writing Stan functions in order to sort of say, okay, what are the distributions that are being assumed for this model, how to draw from the prior predictive distribution. Richard is sort of using the rethinking syntax to accomplish those same goals. And the reason why I think, we're emphasizing the Stan syntax is to put us in a better position starting next week to learn how to write our own models in the Stan language. Whereas, the rethinking textbook, at least the first edition of it, sort of stopped more or less before getting to the idea of, well, could you write your own in the Stan syntax? And so really all these homeworks and stuff, and we'll have another one starting tonight, are more about practicing using the syntax. And so we have a platform to build on when we go to specify our own models. And that's, not necessarily an objective for, all different sorts of classes. But so the rethinking has, lots of good advice in it, but the rethinking book and the rethinking package is good too. It just doesn't do a whole lot to teach you the Stan syntax for doing one of these things. BRMS is a little bit closer, at least in how it specifies the priors and whatnot. So this other person, Solomon Kurz, has written basically like a shadow book that's online that goes along with rethinking, showing how to do, every single example using BRMS and every single plot using ggplot2 stuff rather than basic plots, and does more with like a tidyverse mindset of the sort that is very common today and in data science. And so it's just a different way to specify all the same models. But since we're talking about BRMS last week anyway, it's a bit easier for a class like this to say, okay, here's an example of how to do like each one of these things, and you can literally do every one of them using BRMS, using ggplot2, using tidyverse. That aligns better with the sort of stuff we're doing in the QMSS and the sort of stuff we've done previously in the class than learning another syntax to specify models like this, which is used in the Rethinking package proper, which you can get off GitHub, and we'll need some data sets for it today, but is, in my view, a little bit of a dead end in terms of, okay, you learn how to do it, and then how do you make the next step? Where's the next step to go? It's not exactly a great bridge, or at least the first edition was, to doing things in Stan. And so we're just going to do a bunch of examples that originally were in the first edition of the Rethinking Statistics book, and then taking this stuff from Kurz as to how to do them with BRM. So the first is about tadpoles that live in tanks, and the question is, what's the probability of survival, and how does that vary from tank to tank? So we get the Reedfrogs data set from the Rethinking package, load up BRMS, we put into the data set an indicator for which tank is which, just numbering them 1 to 48, and then we specify a binomial model in the BRMS syntax, the number of survivors, the number of tadpoles in the tank originally, and this is just going to be a flat model. So we're going to use the tank ID variable as a factor, and then each level of the factor is going to get a coefficient on that dummy variable, which has an expectation of 0 and a standard deviation of 5, which is certainly weakly informative, and then class equal B saying that's what it pertains to. And the results that come out, something like this, it's sort of similar if you were to do a fixed effects analysis in economics with a separate intercept for each of the 48 or the 50 states, depending on how you count. Now, usually we would add more predictors and stuff, but this is sort of like the basic model, whatever political preferences or something like that vary from state to state. And so we want to capture that with the intercept. Your probability of surviving if you're a tadpole, depending on what is the nature of the tank of water you live in, can vary from tank to tank. And we certainly expect there to be correlation within tank. Like, what if the water gets contaminated? What if there is a shark in the tank? All these sorts of things would definitely induce correlation among the tadpoles within a tank, but across tanks, it's reasonable to assume conditional independence here. And so this is more or less what it would look like if you did it with GLM. But question.
You have the response part survive given trials. Why don't we do that with the traditional intercept if it's on tank?
We're going to do that next. But the thing to the left of the tilde is a special BRMS syntax for specifying binomial models that doesn't exist in like GLM or any other R package. It's just a sort of quirk with the BRMS. If we were doing this in RStanArm, you do like cbind, survive, die. Anyway, it's just a different way of specifying that. But the question you were about to ask is really on this slide, which is specifying in a more LME4-ish syntax, which RStanArm and BRMS both picked up, saying, okay, same thing to the left of the tilde, but now on the right, we're saying, okay, there's an overall intercept, which is tilde1, and then plus in the parentheses there, we're saying, okay, there's a deviation in the intercept for the log odds of survival, 1 for each tank. And we're going to put a normal 0, 1 prior on the overall intercept, and a Cauchy or half Cauchy 0, 1 prior on the standard deviation as to how much these intercept deviations differ from one tank to the next. And so you can interpret the, well, not the half Cauchy, but the unrestricted Cauchy. 1 means it's going to have an interquartile range of 1. It's a little bit different when you do the half Cauchy, but anyway, this is a prior with a long tail as to how much heterogeneity there is, how much the intercepts differ from one tank to the next, and we're going to estimate that along with everything else to get a posterior distribution of that heterogeneity. Can't talk today. So anyway, in the thing for population level effects, we get an estimate of the intercept, posterior mean of 1.3 there, and then the posterior standard deviation of the variation in intercept deviations from one tank to the next has a posterior distribution of 1.62 and a relatively small standard deviation, and so much more concentrated than the half Cauchy 0, 1 prior that we started with on that as a result of conditioning on, you know, all this data and the 48 tanks of tadpoles that we have. And so we get posterior distribution on all of this with which to make inferences. So does that answer your question? The first thing was really a straw person. This is a much better way of formulating the model. However, if you go to do model comparison, expecting it to say, this is a much better way of doing the model, what you get is all kinds of warnings. So why would that be the case when you go to do, you know, LU, expected log predicted density stuff on these two models that we've estimated so far? Within data, so yeah, you may very well be overfitting in this first one, but you can't actually tell because it's say the warnings make this so it's unreliable estimator of the expected log predicted density, but you should assume you're overfitting with the first one, the fixed effects model. So this has to do with this idea we're going to estimate the effective log predicted density using leave one out cross validation or approximation to leave one out cross validation. And if we were to leave one thing out from these data sets, each observation is a tank. And so if we were to imagine what would happen if we left a tank out, that would have a not small effect on the intercept or the intercept deviation for that tank. We've gone to, you know, estimating everything like reasonably well, but if we were to leave out tank 6, then the posterior distribution of the intercept deviation for tank 6 would be a lot different because there would be no information on it. And the assumption underlying the LU cross-validation estimator is that you could leave out one observation and it wouldn't have a huge effect on the posterior distribution of anything. If it's just kind of a slight effect, we can fix that by reweighting. But if it's a huge effect or a moderately huge effect, then we can't. But if we were to leave out one tank, then the posterior distribution for that tank would just go back to the prior distribution for that tank, which may be a lot different from the posterior distribution we're doing now. So all these warnings are basically saying, you know, can't really do the LU cross-validation estimator effectively if what you're thinking about is leaving out one tank. What you could do, although this changes the question, is explode the data set to have one observation per tadpole and do a Bernoulli model rather than a binomial model and change your question to what if we left out one tadpole. but kept the same tanks, which is similar to the question that you were asking at the beginning. Like, what if we kept the same teachers, but we left out one student? Okay, now you're saying, how well do we expect in terms of log predicted density to predict a future student, rather than saying, how well would we expect to predict the performance of a future teacher that we haven't observed yet? So it changes the question, but it does change the question into one that is readily answerable with the Lu stuff. So we just take each row in the original data set, copy it, however many tadpoles there were, say, you know, which are the ones that survived, which are not. So now we have a much bigger data set, and we do it with family equal Bernoulli at the tadpole level rather than the tank level, but we can keep all the same syntax for the formula and keep the same syntax for the prior. And now we can do Lu for what would happen if we left out one tadpole, and like, it's all fine. There's no warnings. That's because leaving out one tadpole has very little effect on the posterior distribution. We can overcome that with weighting. Leaving out a whole tank would not. And so you have to keep in mind, are you interested in evaluating these models as to how well they predict at the higher level or at the lower level? And different situations, you know, sort of require different techniques. So one thing that you could do, instead of changing your question to what if we left out one tadpole, you could keep it, well, what if we left out one tank, and do k-fold validation with 48 folds, one for each of the tanks. And so it would literally leave out one tank, re-estimate the model as opposed to doing the leave one out cross-validation estimator of what would happen, refit the model 48 times, and you get back this. In this case, I would like get an error when I knitted it, but not when I ran it interactively, and I couldn't figure out why that would be the case. But hopefully it will work for you when you do, you know, something like this. So Lu and brms and RStanArm also support, you know, genuine k-fold, whereas if you sort of set k to be equal to the number of tadpoles, then that would be sort of equivalent to leave one out cross-validation at the tadpole level. So always keep in mind at what level you want to evaluate how well does this model expect it to predict future data. Because in multi-level models, you can do the predictions at different levels. So this is a ggplot version of one of the things in Kurz's book based on Rethinking Statistics book, has a similar thing with just base package. And you can see in tanks that are small, which is to say they don't have that many tadpoles in them to begin with, the degree to which the posterior distribution, which is represented by those circles, is pulled toward the overall mean, which is like maybe a little less than 0.8, is greater in the tanks that are small and have fewer tadpoles than it is the tanks that are medium or large that have more tadpoles in them. And so if you have a tank that only has like 5 tadpoles in it, your unshrunken estimate of the proportion of survival is going to be more noisy than in a tank that has a large number of tadpoles in it. And this is basically what we want to have happen when we don't have as much information from a particular tank because it's small. We want to be borrowing more strength from our collection of tanks as a whole. And when we have a lot of information, because there's a lot of tadpoles in it, just the data alone gives us a pretty good estimate for the probability of survival in that tank. And so we don't need to borrow as much from similar but not the same tanks. And the idea of a hierarchical model is we can estimate the extent to which we need to be partially pooling information at the tank level in order to do this. Now, that has the consequence that your predictions in the small tanks for the tanks that you have are not as good as if you just like looked at the proportion of survivors in that tank. But another way of saying the same thing is you overfit the existing small tanks less and fit tanks in general better. You fit better future tanks from the same data generating process of, you know, tadpoles every year. And so don't get confused by saying, oh, if I just use like, you know, 3 out of 5 tadpoles survived in this, you know, small tank, I can fit that tank really well by saying there's a 60% chance of survival. But you're not caring usually that much about a random tank of water, or it's not even random, but arbitrary tank of water. You're interested in more the data generating process rather than the particular data that you condition on. And the thing about multi-level models is they estimate the degree to which you should be, you know, partial pooling, borrowing, string, and they overfit the existing data less, and they fit future data better. They fit the data generating process better than if you'd done, you know, no pooling or, you know, fixed effects model or something like that. And so that's why we want to look at these measures about how well is this expected to predict future data, because how well it fits the data that you have isn't a primary concern in a lot of situations like this. You only care about how well it fits the data that you have as some sort of indication as to how well it sort of fits data from this data generating process generally, rather than the particular sample that you have or the particular way in which you've separated it into training and testing if you're taking a more supervised learning approach. So as I alluded to on Thursday, these multi-level models are really not a thing in the supervised learning landscape. They do not lend themselves well to getting good estimates of the parameters of these things just by optimizing. If you include like a separate intercept deviation from each tank, the optimum, the mode is not a consistent estimator in the frequentist sense when the number of parameters to estimate is not fixed. And so, you know, we've sort of alluded to maximum likelihood. It has these good properties across data sets, but that, you know, comes along with a couple of assumptions that are important but aren't talked about as much. And one of those is that you know, the estimate has to be interior to the parameter space. A lot of times with hierarchical models, if you just find the mode is on the edge of the parameter space, and you can't have a normal distribution if you can't go like below 0 on one of these variances. So that's one of the assumptions. And another one, the number of parameters needs to remain fixed as the number of observations goes to infinity. And if you're thinking about a data generating process is, okay, we get more and more data by including more and more groups, by including more and more tanks, as opposed to including more and more tadpoles within the existing set of 48 tanks. If you're thinking about, okay, the data sets gets bigger because I get more and more tanks, then there's more and more tank-specific deviations to estimate, in which case the number of parameters to estimate is growing at the same rate as the number of tanks is, and the maximum likelihood isn't consistent. And so even if you do this in a frequentist framework with LME4, they're not maximizing the likelihood with respect to the tank-specific deviations. They're integrating all those out and then maximizing the likelihood with respect to the population parameters. That makes it a well-posed optimization problem, but it does not lend itself to quantifying your uncertainty about at the tank level, because you've integrated out the thing that you want to express your uncertainty about. And so like the number one question that they get on the LME for, you know, discussion forums online and stuff like that is, well, you know, where are my p-values for the, you know, random effects? And not understanding that the reason why LME4 is not giving you p-values for those things is because it didn't estimate them. And the reason why it didn't estimate them is because they're not parameters. And consequently, they got integrated out of the likelihood that was then, you know, maximized with respect to the things that are parameters. But anyway, you don't have to worry about all that stuff if you just take the Bayesian approach. And one of the things that you might want to do is get the posterior predictive distribution for a new tank, a tank that you haven't observed yet. And this is, you know, one of the areas where the Bayesian approach really shines, and where the supervised learning, like all the machine learning stuff, just falls flat on its face. It's really bad at trying to get some sort of a prediction for, you know, something that it hasn't seen data on yet. It's like, you know, you train this thing to play chess, and then you say, okay, you know, we have this really good chess playing computer, and then we say, you know, how will we predict it plays checkers? And it hasn't optimized itself for playing checkers. And so you just get like nonsense predictions. Same thing when you see an image, or you give a computer an image for something it hasn't seen before. It's like banana or something like that, just because it can only sort of refer to what it's experienced. But if you do this for tank 49, when there were only 48 tanks originally, then you can do that. You just create a new data frame with a new label for the tank factor and specify, okay, how many tadpoles are going to be in this tank? Let's say 20. And then you can call posterior predict. You do have to specify this new thing that says allow new levels equal true to avoid the error message. But then you get, you know, S draws from the distribution of a new tank. And you can see what's the probability of however many of the 20 tadpoles in that new tank survive. So there's like almost 15% chance that all of them do, pretty small chance that none of them do. But the overall, you know, mean is going to be around, you know, 14 or something like that. So yeah, you can totally do that with RSIN-ARM, with BRMS, with the Bayesian approach generally. Get the posterior predictive distribution at either or both levels in a multi-level model, or however many levels there are. You can get a prediction at any of those levels just by, you know, drawing from the distribution of the parameters. And then in this case, it's drawing from the same distribution you used as the prior on the, or the same family normal for the tank deviations. It's just using the updated posterior distribution of the, where'd it go? Of the standard deviation that captures the heterogeneity across tanks. So rather than using the half Cauchy 0, 1, it's now using this posterior draws on the standard deviation of the heterogeneity from one tank to the next. Okay, did that. Okay, so that was a model that just had variation from one intercept to the next. What if we wanted to do a model that had variation in the intercept and the slope across groups? So a way to draw from that prior, so this is only drawing once, but let's say we have n tanks, or in this case, it's a hypothetical example about having cafes and how much time you have to wait to get your coffee order, depending on whether it's the morning or the afternoon. But anyway, it's just a hypothetical example. And both the intercept and the slope of the is it a morning or afternoon variable can vary from one cafe to the next. So there's going to be n cafes, and we want draws in the intercept and the slope for each cafe. And so we can draw from the prior distribution on the upper level parameters So for this like population, so to speak, of cafes, you know, A and B just coming unrestricted from normal, sigma A and sigma B coming from half normals. You could obviously change all of this. A row restricted to be uniform between -1 and 0. That captures everything we need to make a 2x2 covariance matrix, which we do here after establishing the covariance is equal to the product of the standard deviations times the correlation. We make our 2x2 covariance matrix. We take the Cholesky factor of that, and then for each of the n cafes, or n whatever the units are, we can take a draw of the intercept and the slope for that cafe from a multivariate normal, in this case just bivariate normal distribution, parameterized in terms of its Cholesky factor with location. And so we can draw from that n times, fill up the rows of our draws matrix, and then return it out at the end. And so this, you know, we did really something like that on the last homework, drawing from bivariate normal county by county. So now we're drawing bivariate normal cafe by cafe, but perhaps this is better illustrated as to how you could extend this from, you know, 2x2 or bivariate normal to multivariate normal. Indeed, we're already using multivariate normal. We just happen to be using it in the case of a 2x2 covariance matrix. And that's all well and good, but that's just drawing from the prior. How will we draw from the prior predictive distribution of waiting times to get coffee at these various cafes? So now we need another function. It takes in S and N, and whether it's morning or afternoon, and a rate for this standard deviation of the errors parameter. So we set up S by N matrix to hold our draws of waiting time. We loop over the simulations, call the function that we wrote on the previous slide to draw the intercept and slope for each of our N cafes. Draw once for sigma from the exponential to get standard deviation of the errors. Then loop from one cafe to the next again, taking the appropriate row out of our draw of the cafe specific parameters. So cafe specific intercept, cafe specific slope on the morning or afternoon thing. That gives us a conditional expectation mu. And then we draw a waiting time from that conditional normal distribution with that cafe specific mu and overall sigma, although we could easily modify this to allow sigma to vary from one cafe to the next. Might be overcomplicated, but we can do it. And then, you know, we return our draws from the prior predictive distribution out at the end. So as usual with the prior predictive distribution, we need to draw from the prior and use those realizations to draw from the distribution of the observables. It's just in the case of a multi-level model, we're going to have priors, you know, on sigma A, sigma B, rho, etc. at the top level. And then conditional on those, we're going to have prior multivariate normal on the intercept and slope at the cafe level. And then conditional on our cafe level parameters, we get observations on waiting time by cafe. And so there's no actual data to go along with that example, but an example with similar structure can be used for a data set that's been analyzed many times about admissions to a university in California by department. So they sort of were scrutinizing their practices for discrimination and whatnot. So 6 different departments, and then there's sort of admission rates between men and women. We set up a binomial model. We have sort of this overall intercept, overall across departments sensitivity to the gender of the applicant, and then we want the sort of log odds of success to vary from one department to the next. That's why we have the 1 inside the parentheses, and we want sort of the potential discrimination based on gender to vary from one department to the next. Data is the same, family is binomial. Now we have priors on the intercept. So actually in the example, they use 0, 10 here, which is ridiculous for binomial data. So I shortened that down to 2 and have standard normal prior on the coefficient there at the university level. But what's different is now, because we have 2 things, an intercept and a slope, that are varying by from one department to the next, we need a 2x2 correlation matrix and 2 standard deviations in order to build that 2x2 covariance matrix. And if we had more predictors, then it might be 3x3, 4x4, something like that at the department level, an intercept and all the slopes that we need for these sorts of things. And so BRMS, much of Stan, our Stan arm, etc., utilizing the LKJ prior on correlation matrices, this with a shape parameter of 2. And so that's going to have a mode at the identity matrix. If it was 1, it would be flat over the space of correlation matrices. And then again, this half Cauchy thing on the standard deviations. If we have a realization from the correlation matrix and 2 standard deviations, we can build a 2x2 covariance matrix to use as our priors on the intercept and the slope at the department level for things like this. And so that is all pretty straightforward. Trying to think if there was anything more I wanted to say about this example. Oh, yes, I did want to say something more. Notice that there's only 6 departments. And this is, in particular, is a situation in which you'll see people do this from a frequentist perspective, but you'll also see saying, you can't do LME4 or SAS prox mixed or, whatever, it's the same algorithm in a bunch of other software when you don't have that many levels of the group. So we're trying to estimate, a correlation and like 2 standard deviations at the university level, but we only have 6 groups, 6 departments. So that's basically like 6 data points with which to estimate 2 standard deviations and a correlation. And they're saying, you need way more departments, way more groups to be able to estimate that reasonably. And that's like pretty true from a frequentist perspective. From a Bayesian perspective, it's not essential. Like you have as many groups as you have. You have prior information about the parameters, which helps to regularize the whole thing. And so this LKJ prior with the shape of 2 is basically saying, okay, the modal correlation matrix is around the identity matrix, which is information that LME4 is not utilizing. And so here you're saying, okay, I don't think the departments vary that much in their intercept and slope deviation from, the overall characteristics of the university, which is probably a pretty, reasonable assumption to be making, particularly if, you only have a few groups. You basically don't have that much choice if you want to get reasonably precise estimates to put in at least a weekly informative prior to rule out a whole bunch of things that you think are implausible on its face, like having the intercept and slope be perfectly correlated or something extreme like that. And so you can see the results either overall or, we call COEF, you can see them for a particular department. It got chopped off, the slope, but basically it did a lot more precise at estimating the intercepts than it did, for estimating the sensitivity of admissions practices to gender. Hard to say a whole lot on the basis of this as to, whether or which departments might have been engaging in discriminatory practices when, the posterior estimate for all those things is very imprecise. And so maybe you didn't really learn what you were setting out to learn, but you learned that you didn't learn that much, rather than just getting like total noise point estimates. And then, finding one that has a p-value of like a little less than 0.05 and then publishing it in some bad journal and then finding out that it doesn't, replicate the next year where they, do the study, things like that. Doesn't talk about this in chapter 12 that we read. It's in chapter 13. So if you're interested in this, you can read about that in the second edition of the book, which is, available online, as we talked about before. So Gaussian processes is not helpful name for a very helpful and useful type of model specification that can be done with a full Bayesian thing. You see this a bit more often, at least if you look on Google or whatever, for machine learning sorts of things, where it's sort of similar setup, but obviously not using MCMC to estimate the posterior distribution of the models. But you can think about Gaussian processes in a number of ways. And it doesn't have to be like a time series in order for you to, so you can do this totally with like cross-sectional data. So one way to think about Gaussian processes is that they're a prior over unknown functions. So from a Bayesian approach, you can say, I'm uncertain as to what is the function governing the relationship between the conditional mean and, whatever predictor. And say, okay, I have a prior over these functions, and I want to integrate that out, the unknown function, and just be left with the posterior distribution of the other parameters. And so one very useful way to think of Gaussian processes is prior over unknown continuous, smooth functions, but otherwise not requiring things to be like exactly linear or quadratic or anything like that. Indeed, sort of taking a prior that puts an appropriate amount of probability over the space of all sufficiently continuous functions. Another way to think about Gaussian processes is an extension of this idea of hierarchical models, allowing the intercept or the slope or whatever to vary continuously according to a continuous predictor, rather than just saying, okay, we have deviations in the intercept and or the slope or whatever according to the group. So we talked about the previous models that we've been talking about, which again are overlapping with the sorts of models that you could estimate a hierarchical model from a frequentist perspective, but going beyond that. And this is one of the areas in which you can go beyond that and say, okay, well, if these hierarchical models that you can estimate for frequentist, it's like for two-stage cluster sampling, when basically you have an interaction between the group indicator and the intercept and the slope, or whatever it may be, but an interaction with this discrete factor variable, whether that's the school or the state or the tank that the tadpoles live in, whatever. You have some categorical variable that you're basically getting interaction terms with, and you have a prior over those interaction terms. Okay, well, if we extend that idea, what if we interact with a continuous variable? That is, it's totally possible to interact two continuous variables with like LM. So is there a way we can get this interaction with a continuous variable and put priors on that? And that the answer to that question, or an answer to that question, is again the Gaussian process. So basically extension of this idea that we were talking about before with parameters that vary according to group. Now it's parameters that vary according to something continuous. And there's lots of examples where this might apply. Indeed, it might apply in any situation in which you're not sure about what is the functional form relating predictors to the conditional mean. In McElreath's book, he's interested in evolutionary biology and stuff like that. So one of the data sets that he uses is this thing, I guess, from someone named Klein, which discovers the prevalence of using tools among like Neanderthal societies or something a long time ago. So there's 10 of those, I think, in the Pacific Ocean somewhere, but on islands, not in the water. And what we're saying with this specification, which you can do in BRMS, can do something similar in our StanR, is saying, okay, there's a Gaussian process on the latitude and longitude of the islands where these people used to live. And saying, okay, the slope relating the usage of tools in these primitive societies has a sort of unspecified but continuous variation according to the latitude and the longitude of their island. And also the logarithm of the number of people they have. I guess the more people you have, the more chance somebody comes up with the brilliant idea of inventing the wheel or fire or something like that. So this is count data. So Poisson, typical stuff with the priors. There's also unknown parameters that go into estimating a Gaussian process that we're not really going to have time to talk about now. But for those sorts of things, it's important to be not specifying improper priors. Like this model does not work if you say, okay, this could be pretty much any function and I'm not, supplying any prior information about it. That just opens up the space of functions way too wide. And indeed, the posterior might not even be proper in that situation. And even if it is, Stan probably won't be able to draw from it without you getting a whole bunch of divergent transition warnings and things like that. So I don't know exactly how they came up with these prior hyperparameters, but they did. And, you get results from a model like that. There were 6 divergent transitions, so I could have increased adapt delta up a little bit higher to hopefully get rid of those. But you can see, okay, here's the slope on the log population. It's positive, reasonably precisely estimated. Here's the intercept. Those are pretty much the same thing as you see before. But you also get a posterior distribution on these Gaussian process terms, which are not really readily interpretable for anything having to do with, okay, if it's this longitude and this latitude, how many tools do I predict for them to use? Better for that purpose to use one of the plots that can be made for models like this that have these nonlinear terms in them. So this is for log. Did it come on the next one? So there were supposed to be 2 columns, but I think it chopped off the second one. Anyway, if you look at the one of these plots for longitude and latitude, or even better simultaneously both of them, you can get a better sense as to how the conditional mean changes as like latitude gets bigger or longitude gets bigger. It wasn't restricted to be in a linear way or a quadratic way or any particular form. It was just restricted to be in a sort of smooth way. And we want this smooth function to run through the existing data points that we condition on. But there's still a lot of uncertainty as to what the functional form is on all the places in longitude and latitude space where we don't have an observation because there is no island there. Or maybe there is an island, but there were no people, something like that. And so because we don't have like all that many islands, we can't be totally sure what this functional form is, but we need to be honest about our posterior uncertainty on that, even after having conditioned on, you know, some data. So we get back, not this plot, because this one pertains to population, but in the same call, it actually generated more plots. You just don't see them here. Unfortunately, if you run it on your laptops, you can. Okay, so out of time for today. We will post another homework tonight. It will involve BRMS and multi-level models, things like that. It'll involve like drawing from a prior predictive distribution. And then we're going to start putting all that stuff that we've done together that might have seemed like unnecessarily large amount of effort in February and March to do these sorts of things when we start learning the STAN language next week and how you could write your own STAN programs in the STAN language by hand, as opposed to merely specifying a function that evaluates the log kernel or draws from the prior predictive distribution, like how to specify a whole STAN program. That's what we'll start to do next week. So check out the reading for that, and I will see everybody then.